Let's digress briefly to talk about the definition of uniform convergence, because that's a big concept that's coming up here. I'll wait to make another video that goes more into detail about this and maybe another problem set. But there's two very related settings. We would say that a sequence of functions f sub n converges to f uniformly on, let's say on R to be simple. Okay, so they're both functions on the reals. What does that mean? It means that for all epsilon greater than 0, I'm going to write out the definition and draw a super crucial picture that helps you understand it. For all epsilon greater than 0, I don't want to use fancy symbols. There is a big N, and that's in the natural numbers, so that just means a whole number, such that if little n is some number that's bigger than greater than n, then, and x is anything in R, then the difference between fn of x and f of x is less than epsilon. Another way to say that is that, well, you could, I'd like to say something like the maximum value of the absolute value over all x in R of the distance between them is less than epsilon. And this kind of emphasizes that you look at all the x's simultaneously and you get one number, which is the maximum distance. So it says a way to measure the distance between two functions is take the maximum of the distance from one to the other. I need to change that in a second. But here's f, for example. That's our target function. And then we would say that f sub n, let's say this is like f sub 1000, that would be close to f if the maximum distance, maybe right here is where the maximum is small. So it's usual with a convergence kind of statement. I give an error bound in terms of how far away I allow the outputs to be from each other. And then if you can respond to that challenge by saying, okay, as long as you go out far enough, and this is the idea of far enough, then beyond that level, you're always going to be within that level of closeness. That's a convergence statement. So you can't really do this, you don't usually see this with a max, because this might not have a maximum. It might be hard to calculate exactly what well, it might not have a maximum, and I don't want to go into the subtlety of that right now. You could do this with what's called the supremum, okay? But that's really not super important in the technical definition. Another really good picture, though, is to take your function f that you want to converge to and pick some particular epsilon and then draw a little band around it. And what this says is that eventually you can pick n big enough so that everywhere after that n, 1,000, a million, a billion, forever after that, you are trapped in that band. If you can do that no matter how small you make the band, then that's uniform convergence. So this picture, this is the picture you want to have in your head. This, when I say the words uniform convergence, I picture a function and these little dotted lines making a band around it. Okay, we're actually using a slight variation of this. We don't actually have a sequence of functions indexed by integers right here, although we certainly will talk about that. Just the way we've got our functions is it's a family of functions indexed by real numbers, because we're sliding them back and forth using a real number parameter. And so we would say f sub t goes to f sub t naught, where this is a real number parameter, and this would be as t goes to t naught. It's just the same thing, same idea. For all epsilon greater than 0, now instead of saying the n, the sequence parameter, has to go off to infinity, I want to say by making little t close enough to little t naught, then I can make sure I could get in that band. So this is for all epsilon greater than 0, there is a delta greater than 0, such that plays the role of the big N, such that if t is really close, delta close to t naught, and x is anything in R, then f sub t, this variable function, evaluated anywhere, is going to be super close to f sub t naught. So it's the same picture. We have f sub t naught that we want to get next to, and then we say, okay, right now I'm looking for 3 decimal places or something. I put this is the epsilon, the width of that band up and down, and I want to make sure that when t gets really close to t naught, I can get very close to it. So I just wanted to actually trot out in slight generality the actual definition. Now, why do we expect this to be true here? Okay, we'll prove this in a minute. If I have some decently nice function, hopefully, what am I doing? I'm not moving it up and down here. I was actually sliding it left and right and just making an exact copy of this guy. So this is like g check translated by t naught. Oops, that should have been blue. Sorry. And this is g check translated by t. One hopes that unless it's a particular kind of a bad function in some way, that if you slide a function left or right, then it's still going to be inside some sort of epsilon band of the function you want. And so that's a good picture to have in mind, that we're actually sliding left or right, but hopefully we can prove that that also means it's not shifted up or down too much. Okay. Right now, though, the task is we're going to assume that we can actually prove that for a sec. We'll postpone that task, as we often do in mathematics. We don't do everything in the order maybe that it's presented in. We kind of cherry pick and do the easy stuff first, maybe. And so let's assume for a minute that we have shown that, and that's just a function. That's just a fact about test functions. It has nothing to do with distributions or integrating against distributions or anything. It should be just a fact that says test functions are nice in some way. So assume that g check t, I guess I was putting parentheses around everything there, goes to g check t naught uniformly. So that's that picture, that it actually stays within that band as t goes to t naught. And now can we show that the f star g, okay, that f star g of t goes to, right, that f star g of t, getting confused here, sorry, just looking at something else, is continuous. That's what we were trying to show. Okay. So let's look at it. Okay. So what's the ingredients here? G is a test function. Okay. And let's say it's supported. It's compact support, which is always at least convenient, sometimes crucial. Okay. And T naught is a real number. Okay. And we want to show that F star G of T is continuous. Wow, that's totally screwed up the O's and the U's there. Specifically at T naught, just to make it more specific. Okay. Now, the support thing, even though it's a nice condition to have, sometimes we have to be a little finicky with, like, the details of that. It's almost never the important thing. Okay, but so we're sliding G and we're doing the check of it. Remember, so let's just do a little calculation about supports. The support of this flipped and shifted version. Okay, that's inside. What is this? It's the set of tau such that T minus tau, because that's what actually gets put into G, is in the support of G, and that is the interval between T minus M and T plus M. Okay. The key thing here is that the T is going to be, we're assuming it's really, really close to T naught. And so this is really going to be a fixed interval. It's not going to move around wildly, so it's not going to be super important. Okay. All right, so as usual, let epsilon greater than 0. Okay, look at some sort of error bound that we can assume we're inside of with the function, with the variable function g tech t, because that's a variable amount of translation. And let's just say this, it's always epsilon that's small that's the interesting part. Let's just say that's less than 1 for convenience. If we wanted to be really careful about this, we would have to prove it also works for epsilon greater than 1. But it shouldn't, it's never a problem to show that something's moderately or sloppily close to something. It's really about the small epsilon that matters. Okay. Make a comment if you think that's something that you don't want me to skip. Okay, so here's a key quantity. I'm going to look at, I'm about to integrate f against g, and I want to show that integrating f against two slightly different versions of g check doesn't make a big difference. Well, it would make a big difference, or the size of the difference is going to depend on how big f is. Okay, so very common thing. We're just going to get some number that measures how big f is, because that's going to come into the calculation. And the epsilon less than 1 tells us that that gives us a little wiggle room, and this should incorporate all of the places where g-check has its support. Okay, so we're taking this guy and we're just putting a little wiggle room on, because we know this should be a t naught, I think I put this wrong in my notes. Okay, and that'll make sure it's in the matches up with the support of g-check no matter how much we shift it. Okay, so now here's the key calculation. Okay, f star g, how are we? Okay, I think I should be able to do this without making it too long. F star g of t minus f star g of t naught. That should be small. Okay, in particular, I want to show that that is less than epsilon. Okay, so what is this? Okay, it's the difference between two integrals. They're written down as integrals from minus infinity to infinity, but as we've often done already, the first thing we're going to do is we're going to chop those down to, this is a t, not a ta. We're going to chop those down to finite integrals. Everything's compactly supported. Well, not everything. F is not assumed to be compactly supported, but G is. See if I can fit it. Okay, that's a d ta at the end there. Okay. And so that's really just going to be absolute value of integral from t minus m minus 1, t plus m plus 1. Same deal. G check translated by this variable amount, and then compared to same deal. I'm just chopping off the supports. And the whole t plus m plus, don't worry about the details of that, is just to make sure that I have something that is a true statement that chops it down to a finite size. And so we just do not have to worry about, oh wait, is this an improper integral? Do I have to worry about convergence? Because sometimes we do. Okay, now I'm going to use the triangle inequality for integrals, which is just what we use all the time. Okay, that's less than if I took the integral of the absolute value of f against the difference between these functions. The key here is that I'm allowing myself to assume, and as soon I will prove in the later step. I know there's a lot of parentheses, but I probably don't need that many, but I will. I'm allowing myself to assume that these guys are small in an appropriate sense. And so small function integrated against a function that we've already sort of got a notation for how big that is. As this gets smaller and smaller, as these numbers get smaller and smaller, this integral should go to 0. Okay, and that's what we want to show, so that the value of t of this function at t and at t naught are getting closer and closer. Okay, so let's see here. Okay, so here's how we're going to use. Let me erase everything but that last line. Okay, we know, or we're assuming that we can prove pretty soon, there is a delta greater than 0 such that So one digression, I hope that writing out something like this, without maybe all the details put in, would be a natural instinct if you're going to prove what we're going to prove, without knowing anything about uniform convergence or anything like that, and you're led to want to show that this quantity is small over this whole interval. And that really leads you to define the concept of uniform convergence. That's kind of the point I'm trying to get at here. There's a delta greater than 0 such that, okay, and this is one of those tricks we're going to do. If you haven't done a lot of epsilon delta kind of proofs, it might seem a little weird. I want this to be small, but I don't just put that it's less than epsilon, because I want the whole thing. I want this whole darn thing to be less than epsilon, because that ties up the proof very nicely. Because if I can show there's a delta greater than 0, such that whenever t is less, such that t minus t naught less than delta implies this. Okay. I want to end up with a statement that says that whenever t and t delta are delta close to each other, this is less than epsilon. And so I can't put epsilon here, but all I have to do is I have to take into account the fact that in a minute I'm going to multiply by I. Okay. So this guy, here's the point, this guy, let me see if I can scoot that in here. Okay. This is the integral of this function times a bunch of variable numbers. But what if I can say that these numbers are never, ever, ever bigger? In fact, let me put an absolute value of here and an absolute value separately here. What if I can assert that the absolute values of these guys are small? Oh, hey, that's exactly what I'm able to do. And it's just a basic principle, back to monotonicity of integrals, really, that if this is always less than epsilon over I, then I just take that out as a constant, and I already had a name for the integral of f of tau. This is just going to be I times epsilon over I, and that's equals epsilon. And now just hide this thing, okay? There is a delta greater than 0 such that when t minus t naught is less than delta, the quantity, the difference between the function, remember this was, I shouldn't have erased it, but I didn't have a lot of room, the difference between f star g of t and f star g of t naught, that's less than epsilon. And that's the continuity of that function. Okay, so it's a good example of taking epsilon delta and those kinds of ideas into the next level. Hopefully, a good transition for those of you who are watching this. And so then we're going to keep going, and we're going to say, okay, we made that big assumption that we could show that G star T and G star T naught really were close in a uniform sense. But it's not really that hard to show that that's going to be true. But it does bring in yet another concept that we'll see in the next video.